Hi, everybody. Welcome to part 2 of the lesson introducing hypothesis testing and the z-test. So we're going to pick up where we left off. But first, just to review, there were 4 major steps in hypothesis testing. We first have to learn to set up hypotheses, and we did that last time. Hypotheses are in the trial analogy. They're essentially you're setting forth the charges against the defendant. Step 2, calculate the test statistic and the p-value. Those are things we're going to learn about in today's lesson. Those are essentially the evidence against the accused. And then we have to state the rejection rule. And the rejection rule is, in the case of the trial, something like find evidence beyond all reasonable doubt. And then finally, state the conclusion in the words of the problem. So last time we talked about step 1 and step 4, and in today's lesson we're going to fill in step 2 and step 3, and then pull it all together into doing a complete example. So the first thing we need to do when we start talking about the test statistic and the p-value is we have to talk about the 2 kinds of errors that might occur when we run a hypothesis test. So let's think first about what the truth is of the population, that H0 is true or that H0 is false. Okay, so if H0 is false, that's what we're looking to prove. And another way to think about that is we're looking to see if there is something interesting going on in the data. We mentioned before it could be some things that we're going to look at later on, whether there's a relationship between 2 variables, where there's a difference between 2 means, or what we're working on now, which is whether the population mean is less than, greater than, or not equal to some hypothesized value. So based on the entire population, is something there or not? And then there's, we take a sample and then we run our hypothesis test. And the conclusion of the hypothesis test could be that we reject H0. And language we use to describe that is when we reject H0, we say that the test is statistically significant. Or if we fail to reject H0, we say it's non-significant. Not insignificant, but non-significant. And so the hypothesis test is really telling us, if you reject H0, it means it looks like there's something going on. Whatever it is you're looking for in the data, it looks like you see it. Okay, the test reveals it. And when you fail to reject H0, it makes it look like it means that the test doesn't detect it. Okay, it's similar to like if you get a test for COVID, for example. You could either have it or not, and that's based on the truth. And the test could either find it or not. And sometimes there are errors. You hope it's right. With the COVID tests, they are right most of the time. So let's start by looking at the event that H0 is false. So if H0 is false, we hope that we would reject H0. And if that's the case, then we have a correct conclusion. Assuming, though, that if H0 is false, the test returns failing to reject H0, that's called a type 2 error. And we consider that to be bad. All right, so if we look at, if we put it in the context of the court case, if we say that H0 is innocent and HA or H1, they're the same thing, is guilty, A type 2 error would be H0 is false, meaning the person is guilty. Would be person is guilty. But we failed to reject H0, but we didn't convict. Okay, so the person was guilty, but they were acquitted. Okay, so that's a bad thing. Now, assuming that H0 is true, though, we hope that we would fail to reject H0, and that would be a correct conclusion. If H0 is true, but we reject H0, that's called a type 1 error. And we consider, a type 1 error is bad, but a type 2 error is worse, or a type 1 error is worse. So a type 1 error, in this case, would be that the person is innocent, but convicted. And if you think about our criminal justice system, we have all these laws in place to try to make sure that doesn't happen, because we consider that to be the worst of the two options. So in general, a type 1 error is going to be if we reject H0 when H0 is true. A type 2 error would be that we fail to reject H0 when H0 is false. Right? So let's look at what the type 1 and type 2 errors would be for some of our examples. So these are the same 3 examples that we looked at in the previous lesson. So we set up these hypotheses that mu is equal to 530 versus mu less than 530. Well, a type 1 error would be if we reject H0. So if we conclude that mu is less than 530, when in fact mu is equal to 530. Okay. And to save time, I went ahead and typed these in so I can just unwhite them out as we go. So a type 1 error would be that we reject H0 when H0 is actually true. Okay? And a type 2 error would be that we fail to reject H0, but H0 is false. So if H0 is false, that means that mu really is less than 530, but the test didn't show it. All right? So we'll go through one more of these. A type 1 error is here you reject H0 when H0 is true. So the test shows that mu is greater than 20 when in fact mu equals 20. And then the type 2 error would be that you fail to reject H0 when H0 is false. So if you fail to reject H0, that means that you weren't able to conclude that mu is greater than 20 when it really was. Okay, so you couldn't find that result when it was there. All right, and I'm just going to go ahead and show these. This last one works exactly the same way. The type 1 error is reject H0 when H0 is true. And the last one is that you fail to reject H naught when H naught is false. So what does this have to do with hypothesis testing? Well, the p-value is the probability of rejecting H naught when H naught is true. All right. So for this last one, for example, to find the p-value, we need to assume that mu equals 90, but find the probability that a sample would make it look like mu is not equal to 90. So that's what the p-value is, and it's calculated based on the sampling distribution. And the test statistic is really just a step on the way to finding the p-value. You can run a test based on the test statistic, but in the real world, people just use the p-value. So we're just going to go straight to that. So for the one sample z-test that we're doing in today's lesson, z is calculated. This is our test statistic, calculated as the sample mean minus the hypothesized value divided by sigma over the square root of n. And that should look familiar to you because that came directly from the central limit theorem. So this is our step on the way to finding the p-value. The p-value formula is going to depend on what your alternative hypothesis is. So if I go back up here, we said that there were 3 possible sets of alternative hypotheses. We've got mu less than the hypothesized value, greater than the hypothesized value, or not equal to the hypothesized value. The less than is the lower tail, the greater than is the upper tail, and the not equal is the two tail. So the p-value formula is going to be different based on which one of these alternative hypotheses you find, or that you're looking to test. So this test statistic is the same formula regardless of which one of these alternative hypotheses you pick for your problem, but the p-value formula is a little bit different. So the p-value for mu less than mu naught is going to be the probability that z is less than the test statistic. And if you remember the way we find the probability that z is less than something is norm s dist in Excel with the value we're looking for, comma, true. If our alternative hypothesis is greater than, then our p-value is going to be the probability that z is greater than the test statistic. And if you remember how to calculate a greater than, based on the normal distribution, that's going to be 1 minus norm s dist, our test statistic, comma, true. For the two-tailed, for the not equal to case, we're looking for the probability that our data, or the probability that we would get data at least as extreme as what we got on either side. So we need to find one tail, which is going to be the probability that z is greater than the absolute value of the test statistic, and then multiply that by 2. So here in this formula, let's work from the inside out. The absolute value of the test statistic is ABS of z star, and I should put comma true in there. And that's showing up in the subscript, but that's all right. And then the probability that z is greater than that is going to be 1 minus norm s dist ABS of Z star, and this should go outside this set of parentheses here. And then we want to multiply that by 2, so we have to do 2 times all of that. If you don't understand that, this is one of those cases where it's okay to just kind of copy it and mimic it. All right, so now based on these formulas, and I'm going to try to leave them up there where you can see them. It's one of those times I wish I had a whiteboard where I could put this off to the side and just point to it through class. But so this is our test statistic formula, and these are our p-value formulas. So in this first one, I've added in a few details here. So we still have an economist wanting to know if the price of a flat screen TV has decreased since 2002, when it was $530. So now they've calculated, so based on a sample of 30 recent sales, so 30 is going to be N. The mean was $504. So the mean is 504. And we're going to assume a population standard deviation of sigma equals 44. So our Z star and that's not the same notation your textbook uses. They use an alpha over 2 or something for that. This is just for clarity. So this is my notation, Z star, just to show that this is the test statistic. So X bar, so we're just going to plug in 504 minus the hypothesized value. So 530 is our hypothesized value. Divided by sigma, which is 44, over the square root of our sample size. And let's go over to Excel and type that in. So we need to put parentheses around the top. And parentheses around the bottom. And we also need parentheses around our square root. So that means this bottom one's going to have 2 sets of parentheses to close. So this is our test statistic, which comes out to be negative 3.236. So that's our test statistic. Now let's find our p-value. We first have to decide which one of these formulas are we going to use. Well, all we do is we look at what the sign is here on the alternative hypothesis. This is less than, so that means we're using this formula here. So the p-value is the probability that Z is less than this test statistic we found, so negative 3.236. And in Excel, that means we're going to do norm S dist that value, and I should have put negative 3.2365, so I would consider this a rounding error. So if I was going to round that to 3 decimal places, that should have been a 7. but I'll just add another decimal place instead. But it doesn't matter because over here we're just linking to that cell directly. So we do our norm S dist, and we get that our p-value is 0.0006. All right. So that's our test statistic and p-value for the first example we were looking at. Now let's move on to our second example. And again, I filled in some details. So we know that we're testing whether mu is greater than 20. So 20 is our mu naught. So we took a sample of 50, so n is going to be 50. The sample mean is 21.2. And we're assuming a standard deviation, so sigma. And this is the standard deviation for the population. Is 4.8. So we have to plug into that same formula, which I'm going to rewrite here. So our z star is x bar minus mu naught over sigma over the square root of n. So x bar is 21.2 minus our hypothesized value of 20 over sigma, so 4.8 over the square root of the sample size, which we got to be 50. So 21.2 minus 20 over sigma over the square root of n, and we get 1.7678. So that's our test statistic. And now to find our p-value, we have to go back and look at which p-value formula we're looking at. This one is greater than. So we need to look for the probability that z is greater than the test statistic. So our p-value is going to be the probability that z is greater than this test statistic. And let's see what that comes out to be. This is greater than, so we have to do 1 minus norm S dist. And I'm going to pick that value, comma true. And we get 0.0386. We're going to do something with this once we, here in just a minute. But for right now, we're just calculating test statistics and p-values. All right, so for this example, we got our hypothesized value is 90, so mu naught is 90. Our sample size is 75. The mean, based on our sample, is 87.8. And you may have to read the problem carefully to pick out which one's the sample mean and which one's the hypothesized value. In this case, you need to realize that this sample of 75 is where this 87.8 came from. Whereas up here with the 90 days, that's what we're trying to compare to. And the last value we need in this problem is our standard deviation. This is the population standard deviation of 9.9. We're going to plug into the same formula, x bar minus mu naught over sigma over the square root of n. So x bar, 87.8, minus the hypothesized value of 90 over sigma over the square root of n. And let's type that into Excel. So 87.8 minus 90 divided by, I realize I'm going through the Excel part quickly, so you may need to pause it if you need to see exactly what I typed in. So that's our test statistic. And we get negative 1.9245. And this is that not equal to one where if we go and look at the formula, this is the one that's 2 times the probability that z is greater than the absolute value of the test statistic. So this one then is going to be our p-value is going to be 2 times the probability that z is greater than the absolute value and negative 1.9245. And again, if we go from the inside out, we're looking for the absolute value of that number. And now to find the probability that z is greater than that, we have to do 1 minus norm s dist of that number, comma true. And then we need 2 times that. So we're going to put all of that in parentheses and do 2 times that. Okay. And remember, one thing, don't forget that if you don't put this star in here, Excel can't do multiplication. It doesn't recognize multiplication without this star. So you got to put that in there. So we get a p-value of 0.0543. All right, so now that we're done with the test statistic and p-value, we're almost finished. We need to talk about what's the rejection rule, meaning how do we know, based on looking at the p-value, are we going to reject H0 or are we going to fail to reject H0? So before the researcher runs the test, they decide on what's considered unlikely. And if we go back up here, we said that, and let me go all the way back up here. We said the logic of hypothesis testing is that we want to find evidence that a hypothesis is true. This would be the alternative hypothesis. So we're going to assume the opposite. We're going to assume the null hypothesis and show that the null hypothesis is unlikely. Well, the question is, what do we consider unlikely? Well, unlikely would always be low probabilities. And typically we define that as being less than some given value. The three common values are 0.1, 0.05, and 0.01. Of those three, 0.05 is the most common. So again, this is where this comes from. We're always looking to see that the alternative hypothesis, or that the null hypothesis, would be unlikely to occur given the data we have. So that's why we're always going to reject H0 if the p-value is small. This cutoff point that we talked about for what's considered small is called our level of significance, or this lowercase Greek letter alpha that looks like a fish. Okay, but it's actually alpha. And so we're always going to reject H0 if the p-value that we find is less than the alpha given in the problem. If there is no alpha given in the problem, you can assume 0.05. I want you to know you always, always, always reject H0 if the p-value is less than alpha. It doesn't matter whether you've got an alternative hypothesis that's less than, greater than, or not equal to. It doesn't matter if it's this hypothesis test or some other one that we're going to do in the future. This is always going to be the case. You're always going to reject H0 if the p-value is less than this level of significance or the alpha given in the problem. And here are a couple memes to hopefully help you remember it. I don't always reject the null hypothesis, but when I do, it's because I found a small p-value. You must be a p-value greater than 0.05 because I failed to reject you. Okay, so a small p-value means you reject H0. Otherwise, you fail to reject H0. So let's go through our examples that we were looking at. And I filled in one more detail, which is I filled in what alpha is. So using a 0.05 level of significance, we're going to test the economist's claim. So all you have to do for this step, and even though it's the same, I'm going to insist you write it every single time. Show me that you know it. This will also help you remember it. So reject H0 if p-value is less than 0.05. In this case, the p-value is less than 0.05. Therefore, of our two possible conclusions, and I have these hidden down here, our p-value is less than 0.05. That tells us we're going to reject H0. So if we reject H0, that tells us that there is sufficient evidence to conclude that the population mean is less than 530. So this second conclusion is not the one we keep. Okay? Again, always reject H0 if p-value is less than the alpha given in the problem. Alpha was given up here. This p-value is less than 0.05, so we're going to reject H0, which tells us that there is sufficient evidence to conclude that the population mean is less than 530. For the second example, we assume, or we're going to test using a 0.01 level of significance. So that means our rejection rule is we're going to reject H0 if the p-value is less than, not 0.05, but 0.01. And this p-value is not less than 0.01. And so of our two conclusions that we drew up earlier that were our possibilities, we are not going to reject H naught. So we can delete this first one because we know that with a p-value less than alpha, we fail to reject H naught, which tells us that there's not sufficient evidence to conclude that the population mean is greater than 20. And in this last case, is the population mean differ from 90 days? And here's the alpha, 0.05. Therefore, our rejection rule is reject H naught if p-value is less than 0.05. This p-value is not less than 0.05, which means that we will fail to reject H naught, telling us that there is not sufficient evidence to conclude that the population mean differs from 90 days. For this problem, if they had told us to use alpha equals 0.1, we would have a different conclusion. So we'd have the opposite result. All right, so just pulling it all together into one problem, let's go back to the problem we started with in the lesson from the other day. This is just so you can see a problem worked all the way through. And I know this video is long, but that's because I just want to make sure I give you plenty of examples, which I hope you appreciate. All right, so back in this problem, we had a random sample of 50 pizza deliveries. And they claim to deliver in under 30 minutes on average. The sample has a mean of 28 minutes, so X bar is 28 minutes. And assuming a population standard deviation, so sigma, of 5.6 minutes, at the 0.01 level, so at the alpha equals 0.01 level, is that enough evidence to suggest that the population mean delivery time is less than 30 minutes? So, first step, we set up our hypotheses. We know our alternative hypothesis is that mu is less than 30 minutes, because that's what we're looking to show. And our null hypothesis is going to be that mu equals 30. Our test statistic. And by the way, I want you to write all of this in exactly this order. You state your hypotheses, you state your test statistic, you state your p-value, and then you state your rejection rule, and then you state your conclusion, because that's the logical order of the argument. Is that we state what we're looking to test, and then we look at the evidence, we compare our evidence to the standard of evidence, and then we state our conclusion. So this has to be in order. So our formula was that X bar is 28 minus our hypothesized value, which is 30, over sigma over the square root of the sample size I'm going to type this into Excel. So 28 minus 30 over 5.6 over the square root of 50. We get negative 2.5254. So our p-value is going to be the probability that z is less than the test statistic. And remember, that's because the formula for the less than alternative hypothesis What's the probability that Z is less than the test statistic? You probably want to have those formulas handy where you can see them as you're going through the practice. So negative 2.5254. And that comes out to be the computer's running slow. Norm S dist. Our test statistic, comma true. And we get 0.00578. And we're going to reject H0 if the p-value is less than 0.01. So if the p-value is less than 0.01, this p-value is less than 0.01. Therefore, we're going to reject H0. And say that there is sufficient evidence if this were in any other way of writing, I would be not writing quite so messy. But to conclude, that the mean delivery time is less than 30 minutes. And if you want to write that as the mean is less than 30 minutes, or if you want to write that as mu less than 30, either way is fine, as long as you use correct notation and write the actual mu and not just spell it mu. All right, so that's it. That's all the steps of hypothesis testing and how to do the Z-test. As always, if you have any questions, please let me know.